Yes. Okay. So, if your bandwidth allows, please turn on your video. So, I have some interaction in terms of how you perceive things. Also, if you have questions, please feel free to raise your hand so I can see it clearly. Although, some of you put it in the chat, sometimes it is difficult for me to monitor the chat while doing the lecture. I think Junaid is there, so at the end, he's going to make sure all your chat questions are also answered by me. So we'll do that. Okay, so let's start. So you had 3 days of bootcamp. Today's the fourth day of this week, and then you have a Memorial Day break, and then we will resume this on Tuesday. So I'll see you again on Tuesday for a short time. So that's me. So as I said, today, we were supposed to start with multi-source data analysis and its challenges. Now I'm going to change the order a little bit because I think the data workflow will be better if I introduce the data storage and challenges and then come to multi-source data analysis. So that's what I'm going to do, but it will be just rescheduling the same topics with the same amount of time. So let's recap a little bit on what we did on the last time we met. So we have discussed data, events that gave rise to unprecedented increase in data. And so we were at that time discussing data and analysis. Independently, we have understood the need for transforming this data into various things that are more useful, like information, knowledge, and wisdom. We have also looked at the way in which computer science or computer technology has progressed over a very short span of time. So now we have to bring all this together in a synergistic way to accomplish our goals. So what I want to emphasize is that data analysis is only one aspect of larger scheme of things. That's not the only thing. Needs software as well as data storage and management. So that's what we are going to address today. So data does not exist in its own way. In some way, it has to be stored somewhere. It has to be managed. So there are a lot of technology involved in the storage and management, which is very important from the analysis perspective. If you cannot retrieve your data with high efficiency, then your response time will suffer. If your data is very large, then your response time will suffer. So to mitigate or to make those things better, the underlying technology needs improving, changing all the time. To understand the transform result, of course, you also need visualization. We'll see a little bit of that. You might have seen the evening activity I gave you. We will come to that in the multi-source analysis module, and I'll talk more about it. So again, the reason I put visualization is some of them are compute intensive. Some of them need to stage data from disks to main memory, and all of them requires technology support underneath. So today we'll take a look at data, how we store it, and how do we manage data for any purpose, whether it's for analysis, whether it is for search, whether it is for processing, whatever the end goal is. So the questions that we have to read. So in order to manage and store data, why and how do we need to store data? Why and how do we need to manage data? How do we retrieve, access, store data for processing analysis? So kind of we assume this, we assume things are in a file, we just load the file. Sometimes it is as simple as that. Some other times it is not. So how is application development and usage of data dependent on how it is stored and managed? So there is a tight synergy between these two, and one needs to understand the other. So what applications were the initial drivers for storing and managing data, and what is the current status? So the presentation outline today will be, we will discuss a few things. Data storage, started with flat files and why flat files are still used, but they may not be the ideal way to retrieve data. Then we'll go to the need for database management systems, which was developed four decades ago. And there has been a lot of work done on that, and that is still being used in a very wide manner. So every every system has a DBMS underneath. So we'll understand a little bit more about how DBMSs came to evolve and what is the current relational and object-oriented database systems like. So in order to do that, we will look at the components of a DBMS. What is the model? What is the representation? What kind of query language is used and why? And then we briefly discuss relational DBMS. Why? Because it's one of the most popular systems that's available today, being used today. It's a $5 or $6 billion industry today. There are a bunch of commercial DBMSs that everyone uses. There are also open software DBMSs. And then we'll briefly look at data warehouses and why it was developed. And then also a little bit of GIS and ArcGIS. You know, this is perhaps more close to your area, but I'm not an expert in that, but I'm looking at it mainly from a data storage, data management point of view. And then there is something called the NoSQL DBMS. We'll look at it and then conclude. So this is sort of our agenda for the first part of today, and then we'll break and look at the other modules. Okay, so kind of very high level view is file-based data storage and management implies. So today, as you know, everything is stored in a file. And what is a file? File is a description of data that is stored on a disk or a tape or a USB stick, whatever device you have that is capable of storing data. So once you have information stored in a file, the burden of processing is on the user application. So if you're writing a user application and you need to access a file, you need to know how this file is formatted. What are the fields, what are the records, and how do you read it? How do you interpret it? Without that knowledge, you cannot write any program on that file representation. So applications need to be aware of the file format, irrespective of what format you use. There are many different ways in which you can do that. So remember that the .csv format that you use very often is a predefined format. So when you say data is in the .csv format, it assumes a particular representation in the file where each piece of data or information is separated by a comma. On the other hand, DBMSs mainly came about, database management systems, to free applications from data format constraints. So writing applications on files is extremely difficult, takes more time, incurs more cost, and very difficult to manage and maintain over a period of time. So that's one of the reasons why DBMSs came about. We'll see how it came about and more about. It also reduces duplication of data. This is one of the very important things, data integrity. I mean, just to give an example, you know, you're a student, you know, you use MyMap if you're from UTA, and you want to make sure that when you go and change your phone number or address, it is changed in all the places that it is stored. If it is stored in 3 different places, and if you change it in one place, then there will be inconsistency with respect to your phone number, with respect to your address. So that's a very very difficult thing that one doesn't want, because that comes in the way of management and processing. So duplication of data is not a very good idea. And if it is to be duplicated, then its management has to be done by the system transparently. You should not be involved in its management, because you don't know how many places it is stored. You don't want to go and change it in 5 different places. You have to manage duplications. So internally, we use something called the referential integrity constraint for that. You don't have to know about it, but what is important to understand is the system has to manage it transparently. Then there's the question of querying the data. Once you put data, whether it's in a file or a DBMS, how do you retrieve that data? Not just retrieval, but retrieve in a way that is easy to understand. So for example, you want to retrieve your data saying, okay, I want to see the list of courses I am registered in. I don't want to see anybody else's courses, but if you have to process a file or an application where to process a file, that's very difficult to specify. So we use something called SQL or structured query language for that. We will not go into the details of that, but we'll just indicate how it is different from other ways of retrieving data. So this is known as a non-procedural querying. Instead of writing a program, you write a simpler way to express your intent, and the system is responsible for computing it. DBMS also provides extensive utilities, and that is very useful for the management of data. So we will discuss a little bit of file-based system. We'll discuss DBMSs. We'll also discuss data warehouses, because that's useful, or that gives an idea of what was the first step in the multi-source data integration as well. So it fills a analysis void, what is termed as the multi-dimensional analysis void. It provides new operators such as cube and rollup, combine data from multiple sources. So this is very important. In a single organization or an enterprise, you may have multiple database management systems or even file systems that store different data. And if you want to bring those data together, data warehouse is one way of doing it. So this is typically done within an organization. This can also be done across organizations or across DBMSs. We will not go too much into that detail, but that's a bigger challenge. And then we have seen big data, so we will see a little bit of cloud computing in this topic. Okay, so that's the high level view. So topic is discussed: data storage, files and repositories, data management, relational DBMS, data warehouse. What is a data mart? What is a data lake? GS. No. So if you are to understand that, I think it's important to understand a little bit about what is disk capacity and the cost of storage. As I said in my previous presentation, tape drives were used earlier because they could store large amounts of data, but they were too slow. Not only they were too slow, they are known as sequential access devices. That means you have to go through the tape sequentially to access any data. So if you want a data that is in the middle of the tape, you have to go through the first portions of the tape in order to access that. So that was very inefficient. And that's one of the reasons that disk storage came into being. So disk is what is known as a random access device, which essentially means that you can access any portion of the disk without having to sequentially navigate the disk. So this is very important. I mean, this happens underneath, you don't even think about it. When you are accessing your laptop or when you're accessing any machine which has a disk, you're using the random access. That's why data that you retrieve from the disk is so fast. And there are two different types of disks that we will briefly look at. One is known as the HDD, or the hard disk drive, or the more newer one, SSD, which is the solid state drive. So today, most of the places we still use HDD. Laptops mostly use SDD because they are smaller size and the cost is very high. SSDs are becoming cheaper and more popular. We'll see a comparison, but that there is a huge difference between HDD and SSD in the technology, and SSD can become very fast if we can bring the cost down to use that. So remember, processing always happens in main memory, CPU. So you cannot process anything on the disk unless you bring that information to main memory. So this is a very important thing you should understand. We don't think about it, but we have to what is called load your data to memory before you can do processing. Once you do the processing, if you get results, you have to push it back to the disk to make it permanent. So data needs to be brought to main memory for processing. Disk is just a persistent holder or storage of data. You cannot do any processing on the disk. The next component is the CPU or the processor speed. So today, the processor speed is very high. If you are familiar with it, it is typically measured in gigaflops or even teraflops. Flops meaning floating point operations per second. So that is the unit in which it is measured. And the second component is the memory access speed. So remember, you have to bring the data from disk to memory and memory to registers or CPU in order to do the processing. So there is two levels of access before the data can be processed. So memory access speed today is in nanoseconds, which is 10 to the power of -9, but the disk access is still in milliseconds, which is 10 to the power of -3. So you can see between these two, there's a huge gap. And the gap is, memory is a million times faster than disk. So that creates a problem because, think of it like you have a huge expressway with 10 lanes and suddenly it becomes one lane. So imagine the backup that is created because of the shrinkage or not having the capacity to deal with that. That's very true between the disk and main memory, and we have to figure out a way to address this. And this difference is termed the impedance mismatch. Impedance terminology comes from electrical engineering, but that puts the resistance to move data smoothly between disk and main memory. So this is something useful to understand and remember. So here is a kind of a view of cost of storage. So you can see here this goes from 1956 to 2023. You can also see that the cost of, one is a disk, the other one is a solid state device, then flash, and then memory. So you can see that both disk and memory started early on in 1956. There was no solid state disk at that time. There was no flash memory at that time, and they started very late. Flash memory started around 2000 plus, and solid state devices became popular after 2010. So this is just to understand how technology is evolving. The other thing to note here is the cost. Look at the cost in the initial stages of these devices. It was extremely high, and the reason it was extremely high was because that's why we had very small devices. So this is normalized with respect to terabyte, but there were no terabytes under there. So you can also see how the cost of both disk and memory has come down over the years from almost a very high value to a very small value. Today, you can buy disk for less 1 terabyte of disk for less than $100. You can buy memory, 1 terabyte of memory for maybe it's still more expensive, but you can also see the flash memory cost is coming down. Solid state cost is also coming down, but their sizes are not very high at this point. So this is very educative to see how technology is changing and why what you are able to do today by storing hundreds of thousands of maps and images can be supported because of the technology improvement. Otherwise, it was just not possible. Here is a much closer view of just the two devices, hard disk drive and solid state device, and the cost per terabyte. So you can see that still the solid state drive cost is much higher, $35 per terabyte to $13. So there's a huge difference. Plus, they are not able to produce larger systems. So one thing very important, I don't know how many of you may know the difference between HDD and SSD. Does anyone know the difference between HDD and SSD? There's a very subtle and important difference that makes a huge difference from the access and processing point of view. Now, okay, so at least you know what a disk is. Typically, HDD is a disk that where there is a platter, as we call it, whether it's 2.5-inch disk or 3.5-inch disk or what, that plate is rotating at a very fast speed. So it's a mechanical device. So, and the data is stored on this device and it is rotating at a very fast speed, and the data is accessed using a read head on the platter. So the access time depends upon the speed at which the plate is rotating. And today, we are able to go up to 10,000 RPM. And because it's a mechanical device, there are limitations to improving the speed. On the other hand, the solid state device, as the name says, does not have a moving part. It's purely solid state. And because of that, you can achieve high efficiency in terms of access and retrieval time as compared to the mechanical device. So this is a good thing in the sense if we are able to bring down the cost of SSD and increase the size of SSD, that is going to become a commonly used thing because you can reach much higher speeds than what can be ever achieved using a HDD, because there's a limit on how fast you can spin and still accurately access data from the device. So that's something to remember. So when you buy a laptop, you can see that the cost of SSD is much higher for the same amount of disk space compared to HDD. So CPU and processor speeds have been increasing, and to understand that increase, you should know a little bit about what is called a Moore's law. So Moore was one of the Intel's founders. Intel is the company that manufactures chips, integrated circuits, and everything else that is used in computers. And he stated that the number of components on a single chip doubles every 2 years at minimal cost. While there is no proof for that, this was an observation and extrapolation that has held steady since 1965. So for the last 50 years, they have been able to double the speed of the CPU every 2 years. And that's why now today you can process gigaflops and teraflops that you could not do earlier. That's why the phone in your pocket is more powerful than a supercomputer 30 years ago. However, we are reaching the limits of the clock speed, and the difficulty today to improve it further is the management of heat. I don't know if you have looked at the printed circuit or if you have tried to assemble a computer yourself, you will see that on the CPU, there's a huge thing sitting on that to dissipate heat generated by the CPU. It generates a lot of heat, especially the GPU machines generate a lot of heat. Remember, we also alluded to that in the last lecture, why these server farms are located in cold regions. So heat is a big problem. To dissipate that heat, there are technologies that are being developed. So what is not known at this point is whether Moore's law will hold for the next 50 years, and we'll keep seeing the same computing speed. Today you might have heard of NVIDIA, which is one of the companies that produces the AI chips that are used, H100 and B100, that are really popular, and it's used for not only gaming, but also for scientific research. Okay, that's with respect to CPU. What about disk? So as every piece of data needs to be brought to main memory for processing, disk speed is also very important. So when we say disk speed, it is disk input output, especially for processing where all data cannot be held in memory. We'll come back to this because this is important. You don't have enough memory to hold all the data. Even when you store an image or when you render an image, you can see that the image is rendered in stages because you cannot bring the entire image into memory at the same time. Disk I/O is measured in two ways in terms of input-output operations per second, called IOPS, and throughput, which is the amount of data retrieved or transferred per unit of time. For processing large amounts of data and scalability, throughput is very important, but the sad part is, or the thing that we have not managed to technically advance, is disk I/O has not kept pace with memory speed, disk storage size, and CPU speed. So that is the main problem. So disks have been the weaker links in that chain of things. And so things are determined by the weakest link, and disk is the weakest link, especially HDD disk is the weakest link. So hopefully SSDs will be better once we master the technology better. So that is to just give you an idea of the components, whether it is memory, whether it's CPU speed, whether it is transfer from memory, transfer from disk, and what are the things that are happening and how they're running. So files for data storage. So this is a basic abstraction for grouping or storing information digitally as binary or non-binary files on disk. So everything is stored as a file even today. File size depends on the amount of data stored. A disk holds hundreds of files, and file access table is used, for accessing the disk. So you put whatever files you want on the disk, and there is a piece of software which creates a file access table, or a FAT table it's called, and then used for accessing it in a random time. There is something known as the chunk size used for files have increased over time. So if you have ever formatted a disk, you will know that it asks whether you want to use 4K or 16K or 32K as the size. File sizes themselves have gone beyond 4 GB. Earlier, that was the limit because of the 32 bits used for representing that. Today, we can go to much larger file sizes. Files are very simple abstractions, but are very powerful abstractions. And it has not changed since its introduction in the 50s. All types of information today, whether it is raw data, processed data, or anything in between, are still stored in files. So text, audio, image, video, program, MRI, EKG, plots, visualizations, maps, layers. Now AI created everything is stored as a file. Program is a file, data is a file, the binary code that you execute is a file. So the only abstraction we have for storing data on a computer is a file. Different kinds of files have different formats. So user system DBMS decides how to store information in a file, that is the format of the file. Typically, they are stored as fields, records, pages, and values within a record for structured data. And this layout of the data needs to be known to the application or the program for interpreting that. So briefly, I don't want to bother you with all the details. So if you have multiple fields, so suppose say you have your first name and your last name and middle initials, your phone number, your gender. So these are stored as separate fields, F1, F2, F3, F4. They may have different lengths. So information about field types same for all records in a file stored in system catalog. So this is how a record field within a record is represented. And this is how records in a page are represented. So there is a fixed size page. So don't worry about these details. So just understand that, a page has a fixed size and so many records can be stored in a page, and the file itself is stored on the disk as a header page with pointers to other data pages in the file. So this is how kind of a, files are organized behind the scenes. So when you say load this file or read this file, it goes through the header page, it accesses the data page, it interprets the record, it interprets the field, and then processes the data. So file-based applications need to be aware of data representation or format, because that format can be different for different data that is stored, even if they are CSV files. Makes it difficult to change the format once applications are designed. So once you design the application, you cannot change the format, because if you change the format, the application will not work. If the file format is changed or extended, all applications must be redone. Application management is difficult, it's very labor intensive and prone to errors. So there's a strong coupling or dependency, as we call it, between application and the file format. So difficult to manage duplication, because you may have data in different files and you don't know, because somebody has to keep track of which data is duplicated in which file and in what way. So let me sort of give you an example of what was the difficulty in the 70s, in the late 70s. I was part of a payroll processing in India, which was file-based. At that time, disks were still not very popular and did not have enough storage, so we were using tape drives. Multiple files were used to process payroll. One file might have the personal information of the employee. Another file might have had the wages information for each employee. The third one might have had the hours worked by an individual. And all of this information had to be put together in order to generate the pay stub or the pay stub. We were also using tape drives at that time, as the capacity of disks were small. We had to update these files as well and write new master files if successful for the next run. So you run it once a month or once in 15 days. You create a new master, which is used for the next run, and then continue that process. So this process would take at least a day, and maintaining the files for the next run was very critical. And sometimes if the run doesn't go completely, then you have to trash that whole thing and then start with a backup copy to do the whole thing again. So there were additional issues to be considered. In addition to processing issues, there were several other issues that were difficult to manage using the file-based approach, as I indicated: duplicate information, maintaining consistency in the presence of duplication, concurrent usage. So concurrent usage meaning multiple people using the system at the same time. The best example I can give you is the MyMap. So if you are from UTA, even if you're in the other one, you use something similar. So you're all trying to register for the courses. So hundreds of students or even thousands of students are trying to register for the course at the same time. That is what we call concurrent usage. Just imagine a situation where that was not the case. If each person had to do it individually and the next person had to wait for the previous person to finish, then imagine the difficulty and the amount of time it takes to just register for a course. So that's very important. Determining how to combine data was another challenge. Recovery of data in the presence of failures was also very difficult, and querying the data was also difficult. So you had to write a new separate program or application for each query, managing large amounts of data. So this was the initial situation using the files. So people were looking for improvement in this situation to overcome all these things. And that's what gave rise to the notion of a database management system where data can be managed not by a human, but by the system transparently. So before we get into that, let us understand what a data repository is. So a data repository is a storage space for researchers to deposit data sets associated with their research. You can think of it as a data archive or a data library. And now today you use a lot of repositories without even knowing that they're all repositories in your own domain and in various other domains. A data warehouse is also a repository, but the difference is that aggregates data from multiple relational sources or segments of a business without the data being necessarily related. There is also the notion of a data lake. It's a large repository that stores data that is to some extent classified and tagged with metadata. So we will discuss metadata later, and you've already seen the FAIR principles. This is very important. If the data needs to be useful for large number of users, you cannot just put a data set without explaining what it is. So metadata comes in handy, and if you follow the FAIR principles and create your data metadata, then it will be machine searchable and useful for a variety of that. That is the sort of the core of this workshop. Why metadata is important, why FAIR principles are important, why we should adhere to those things. You are, of course, familiar with Git or GitHub, can be seen as another repository for data as well as code. It is typically done at an individual or organization level, can be done in a broader way, is organized, and typically it's used for version control and keeping track of these software versions. So here are a few data repositories from GIS, Geographical Information Systems, I looked up and listed. You may be familiar with many of these. You might have used some of them. There is Natural Earth data, which is in public domain. USGA Earth Explorer data, largest free source of data. OpenStreetMap, which is crowdsourced. Esri, which is one of the companies that is in this space, has a large repository on which you can search using map, topic, and location. NASA collects a large amounts of satellite and other data that is also stored and made available for research. Open topography data, high resolution, spatial resolution. NASA Earth Observatory, one of the largest repositories of climate related. So there are a lot of repositories, a lot of storage. The question is, how can you use it and what kind of information that should be associated with the data sets in order to successfully use it without having to spend a lot of time. So that's where metadata and FAIR principles come into picture. I think that is the theme of this workshop. So that is with respect to file storage and repositories and what is not good about file storage, why it is difficult to use it. So now let us look at the application types. What kind of applications do we typically run? They can be broadly classified into three categories. Compute intensive applications. So that means these applications take a lot of time to compute. So you typically end up loading the data, load all data into memory and process. So wind tunnel simulation is one of them. Various other simulations, numerical analysis, image rendering. Some of these can take from hours to days in order to complete the computation, depending upon the complexity of the application. So this is one form of computation where you have a data set which may not be very large, but the computation is very complex. The second one is, you can call it a data intensive applications, where you have very large amount of data that cannot be stored in main memory. Any Walmart point of sales database, Amazon inventory database, airline reservations, Homeland Security, any of these can be seen as an example. So in these cases, the difference is, instead of loading all data from main memory, you have to stage data. You have to stage data as needed from disk to memory and process in memory. This is where the difficulty comes, because staging data means that you can only bring a small fraction of the data for processing, but this small fraction of data that you process may keep changing over a period of time. That means you have to bring in new data, take out old data, and this has to be managed by somebody in a consistent and efficient way. So that's the problem. The third category, of course, is one that has both the components. So here the data is large, plus the computation is also very large. So you can think of, machine learning algorithms, various analysis algorithms that require a lot of computation and also use very large amounts of data. So this requires the component. So you can only load. So the question is, we know how to do the first category very well, because we can just load data and then run your program. You don't have to worry about it. The difficulty comes for the second category. Here, if you write your own application and if you have to stage data, then you have to figure out how to stage data, and that is not easy. Earlier, some of the programming that we were doing included memory management, and that was pretty hairy, mainly done in C and C++. I don't know we can even do it in Python and other higher level languages. So it is not easy to deal with the second category, and that is where the database management systems came into picture in order to help make this transparent and as easy as the first one. So that's what you need to understand. So how to make use of data easier? There are multiple ways of doing it. Standards for representing data and exchange of data. So if you have only one way to represent data, then it's easy. Every application can be developed, but that is not going to be the case. The second is the use of metadata to understand the data by humans, but this metadata can also be used by programs or applications to interpret the data, and we'll see more of that later. Use of database management systems are DBMS to store and access data. So there's the third way. So what this means is, somebody else is responsible for storing and managing and retrieving the data. You only tell the system what information to store, not how to store. So there's a big difference between what to store and how to store. So what to store comes under your purview. You know what information you want to store, whether it is course information, whether it's registration information, whether it is demographic information. But how to store it is something that you don't want to do. If you do it, then you are doing like we discussed as a file. There are also data exchange formats that have been developed more recently. XML is one of them. You might have used it. JSON is another one that has become more popular because there are programming language support for that. Related issues to use of data is the notion of interoperability that we will study later today in this module, in part of it. Okay, so let us look at why database management systems were developed in the 60s and 70s. So they have been around for a while and they are still being used. That means there is some utility to them. So DBMSs came about to overcome difficulties associated with processing data from files. So all the difficulties that we discussed were becoming larger and larger. So we needed something better. So this was done by decoupling the data representation from application. So one idea was to separate these two. You have a representation, you have an application, but application need not know the representation. Now, if application does not know the representation, then there has to be something that manages or maps that in between. So that is the thing that, so this is a very common practice in computer science. You add a level of indirection. That means you hide it from this end, but there is a piece of software that manages that mapping from this to this. So adding a level of indirection or middleware or agent, we'll discuss this further as part of integration. This requires software which can bridge this gap. This is done by providing a higher level of abstraction for the user. And this abstraction is mapped. When we say map, meaning stored in files using that software. Think of it like a compiler. So what does a compiler do? You write a program in Python, but you cannot execute Python on any machine. You have to convert it into machine language for execution, but you don't know the machine language and you don't want to know the machine language. So the compiler converts this Python program into machine language. It doesn't have to be Python, it can be Java, it can be C, C++, anything. And then it is executed on. So this conversion mapping is done by a piece of software. And writing a compiler is not easy. It's a very complex piece of software. Similarly, DBMS is a complex piece of software. Just to give you an idea, Oracle, for example, has more than 1 million lines of code. 1 million lines of C, C++ code for managing it. I'm sure ArcGIS has similarly million or more lines of code for managing it. So what is important here is this abstraction, higher level of abstraction. You have to have a higher level of abstraction that you can deal with, and then it is mapped. So a relation was used as a higher level of abstraction for the relational model. For the hierarchical database, something else was used. For network database, something else was used. So it had mathematical underpinnings in set theory. Relational database management was born, that is widely used. Network and hierarchical DBMS were precursors. So 60s, we saw the hierarchical network DBMS. From the 70s, late 70s, we have RDBMS. Now we have different types of NoSQL systems. Any questions? I know I haven't looked at the chat, so it looks like there is no question in the chat. So anybody has any questions up to this point? Okay. So what are the levels of abstraction? So this is how a DBMS is organized. So you have the disk where the data is stored. And the data is stored in a particular format, which is known as the physical schema. So this physical schema is not known to the user or it's transparent to the user. On top of that, there's a conceptual schema, which is the abstraction we are talking about. And on top of that, you can also have different types of views. I'll give an example later. So provided indirection as discussed in the previous slide. So here are two levels of indirections or abstractions. So a view is mapped to a conceptual schema. Conceptual schema is mapped to a physical schema. Physical schema is stored on the system. All these mappings are done by the software, which is the DBMS software. The user does not have to worry about it. The user has to know only the conceptual schema. So single conceptual schema and physical schema is predefined. Views describe how users see the data. Conceptual schema defines the logical structure. Physical schema describes the files and other things that are used on top of them. So you can also think of the schema as a data exchange format. So DBMS to the rescue of all problems associated with file-based problems. By decoupling the software, this is a common practice, as I said. This requires a data model that is easy to understand, and in addition to the model, you should be able to perform computations, even complex computations on the model. Abstraction levels many times for different purposes. This also requires software. So think of compilers that converts program. Think of web GUI that allows you access by filling boxes instead of writing a query. So today, writing queries is more difficult than filling a few boxes. And that's what you can do on the web. And then internally a query is generated. The result is obtained, again shown to you in a digestible form. This is in contrast to command prompt style used earlier. So earlier, you may or may not be familiar with it. People were doing things on the command prompt, typing every command to do that, which is really cumbersome. Before we had, graphical, I think Windows brought in the notion of a graphical user interface that's being used today. So DBMS can be understood in two different ways. One is from end user's perspective. So if you are a user of a DBMS, what do you need to know? If you are going to be part of the development team to implement a DBMS, what you need to know. So I would think that this group is mainly interested as an end user. You are going to be the users of a DBMS. You're not worried about how it is developed, but you need to understand a little bit of this in order to use it in the best possible way. So understand the need for a DBMS, applications for which it was developed. How do you go from your application to designing a DBMS? So this is very important because it doesn't matter what application domain, even in your domain, if you end up in a situation where you have to develop a system for your application and your analysis and your processing, you need to know this relational model and why it is used and why it is simple. MySQL is used for querying and generating reports. How to use a DBMS, whether it is Oracle or ArcGIS or SQL Server or DB2. So Oracle, you might have heard of. DB2 is from IBM. SQL Server is from Microsoft. ArcGIS is from S3. So what were the drivers for DBMS? So why? I mean, every technology when it is developed. So if it is a compiler technology, there were some drivers that precipitated that development. For operating system, I mean, before the advent of operating systems, people were still using computers, but in a very primitive way. So operating systems brought out a level of abstraction that is makes it easy to use. Compilers brought out a level of abstraction, DBMS. So these were based upon requirements from several enterprise applications at that time. And those are typically banking and financial applications. So if you're using a bank, you need to make sure your data is safe, your data is recoverable, and lots of users can use the data. Multiple users can be accessing the ATM machine. Airline reservation. This is again large amount of data. Hundreds of people can be making reservations on the airline. Employee data management and payroll. This one is something that needs to be kept over a long period of time. So, I mean, what is important is, so even though you are studying today, your records will be kept by the university for a very long time. Just to give an example, suddenly, one day UTA came to me and said, "Oh, we need your transcripts for your PhD degree." And it had been 35 years since I got the degree, and I didn't have a copy of the transcript. So he said, "No, you have to get it." So I went to my university and then asked for that. They were able to send me an official transcript after 35 years. So what that means is the data that was collected during my presence has been kept for 30 plus years or even more. Think of Boeing plane. Each plane is in existence for 30 to 50 years. That means all the details, all the parts and the other things should be available and useful for the 30 years of the lifetime of a system that is developed. So data management is not just for storing data, but managing the data over a long period of time, which becomes very critical in many applications. Managing inventory and other related services. Earlier files were created manually without any principled process and only based on the knowledge of the application by a developer. How many files, what are their contents, what are their formats were sort of determined based upon the experience of the individual who was doing it. This kind of ad hoc design could not be carried over to large enterprise applications with complex requirements. So programming in the small version. So this is the difference. So if you're writing a small program for your personal usage, it doesn't matter whether you use a very principled approach or not, because you are the only one who is using it. But if you're developing a system that is to be used by a large number of users and that is complex, then you cannot just adopt the same methodology for doing that. So what were the requirements? One, deal with large amounts of data at that time. Now, I'm saying that large is a relative term. What was large at that time may not be large today. What is large today is very different from what was large at that time. So this notion of large keeps changing every 5 years, 10 years. So we started with megabytes of data, then we went to gigabytes of data, then we went to terabytes of data. Now we are talking about petabytes of data and exabytes of data. So this is kind of a moving target. Support large number of concurrent users. This is very important. Again, I come to if the university has 5,000 students in the College of Engineering, they will all be registering at the same time. Data consistency. Again, duplication, elimination, data consistency has to be managed by someone, not the individual users. Support different user views. This is also very important for a large system because, so think of it. Think of the environment that you're familiar with. The president of the university wants some piece of information from the system. The provost requires a different piece of information, the dean, the chair, the faculty, and the user or the student. So different students, different people in the organization want to see the same data or portions of the data in different ways. There are also privacy and access control issues in addition on. Not everyone should be able to see everything. Other students should not be able to see your details, your GPA, for example, or your financial payments and other things. So there are issues that needs to be managed and supported. Complete and consistent recovery. This is very important. If the system fails, if there is a power outage at the time you are doing registration, your registration cannot go away. Your payment cannot go away. So that's a very critical fast response time and reduced application. So these were the requirements. And to meet these requirements, DBMSs were developed. So let's briefly take a look at data models. A new approach was needed for taking care of all the complex requirements. First, applications had to be modeled in a systematic way to make sure that data is captured completely along with interrelationship among data. functionality and on the captured data should satisfy application requirements. Data models were born in the 60s, so hierarchical, as the name says, the hierarchical model is like a tree. So you can represent your data as a tree. Network data model represents data as a graph, and relations represent data as a relation or a table. So these were the main models that were used for the database management systems. So this is the one that is widely used today. ArcGIS supports all commercial relational RDBMSs, relational DBMSs, and there are others today. So you might have heard of UML, if not ER. ER is the entity relationship model. So the need and goal was to model real world data as closely as possible and applications developed on top of that using the levels of abstraction. For that, extended entity relationship model or ER was developed in 1970 to capture entities relationships in an organization. It's a very simple model. It's a very powerful model, still being used today for the design of DBMSs. Several tools are available for doing this. Real world objects are modeled as entities and their relationships are captured using models. This model is converted algorithmically into relations. So once you develop this model, which is still a manual process, but you can use tools to do that. But conversion into the specific model, whether it's relational, hierarchical, is done. So here is an example of what a ER diagram looks like for company founders. So you can think of a person as an entity, university as an entity, city as an entity, company as an entity, and these are the attributes. So a person has a name, a gender, person, these are relationships. Person is married to another person is a sibling of another person is a parent, and you can also say a person studied at a university. A university is located in a particular city, and company is headquartered in a particular city. A person is born in a city. This company was founded by. So this is kind of a diagrammatically makes it easy to understand the enterprise as you want to represent it. And I'm not saying this is easy to do. This is just an example, but this is much easier than just arbitrarily coming up with something. And once you do that and verify the correctness of it, you can spit out relations or the relational data model from this using an algorithm. And then you can continue, and then you can load those relations, you can populate those relations, and then you can query those relations in a DBMS. That's how typically it is done. So this is just to give an example. So what is captured in a ER model? So essentially, it only captures the data. So you can see here, it doesn't capture any action. It only captures data associated with the enterprise, and that is very difficult to, that is very important to understand. For example, we do logging into the system routinely. Logging is an action. Now, you don't capture logging as part of the model, but it is an application which uses the data that is stored as part of the model. For example, when you do the login, you provide a username, you provide a password, maybe you use a CAPTCHA. You also have something about how often do you need to change. It may also say you cannot use the last 3 passwords. All that information is stored in the DBMS, and the application uses it to verify your authenticity and login. But the logging itself is an application. So that's important to understand. So the separation between data and computation are actions using the data that is stored. Same thing about an invoice. An invoice is something that is generated, just like a credit card statement that you get every month. The credit card statement itself is not stored in the database, but the items associated with the credit card is stored so it can be generated anytime. Once it is stored, that can also be persisted. So in addition to modeling the data, we need to make sure all needed computations can be supported with the data captured model. This is done using query language or writing applications. If you modeled a database, you should be able to ask a bunch of queries. So if you modeled a library database, you can say which book is borrowed by whom. Other databases generate a report of customers who have not paid the last credit card bill or last two credit card bill. Track UPS shipment to know the current status. What are the 10 most popular movies on any streaming media? Generate honor students in the college opinion. So these queries can be pretty complex, but they are based upon, so you have to understand that writing these queries is not the same as doing an analysis. There's a difference between queries and analysis. Querying is accessing information that is stored in the database. Analysis is more of computing additional information using the data stored in the database or the file. So when you do a statistical computation, when you do an average, you are computing additional information based upon the information stored in the database. So that is analysis is more of a computed information. Whether it is a computed information that is difficult to compute or easy to compute does not matter. UML is widely used, so it's known as the Unified Modeling Language based upon ER. So for people who are developing large systems in Java, for example, use UML a lot for defining or creating use cases for the object-oriented design. So this is used for the object-oriented. It's backed by OMG, has support for user view, behavior view, structural view. For building a JS and object-oriented JS data model and system modules can be implemented. Abstract classes are used. You can export it to XML and then do various things on that one. So this is an example of a UML usage for urban and land management system. Each box corresponds to a class, attributes of the class, and actions or methods to be taken on the class. The lines indicate the usage, that the connection between these two in terms of what information is used. So there are different types of relationship, like has relationship is measured by, they can be expressed. I mean, this is important for documenting what you are designing and what you are implementing so that it can be used by somebody else. So briefly, I think I may be going very slowly. So I'm going to skip some portions that may not be very important. So in summary, a DBMS is a large integrated collection of data. So integrated is very important. You can think of MyMap used by UTA is an Oracle DBMS underneath. Whatever system used for when payment of fees are likely to be DBMS. It models a real world enterprise, in this case, university. So entities are students, courses, buildings, websites, relationships are students take courses, lenders issue mortgages, an employee manages a department. So DBMS is nothing but a piece of software. Albeit it's a complex software with millions of lines of code. And then that sits between you and the actual data that is stored as part of the DBMS. So that is responsible for managing all the data that is stored in the DBMS through user interaction, which can be done using a GUI or in some other way. Why use a DBMS? As I said, data independence. It frees the application from knowing the details of the format. Reduced application development time. Because of that, supports data integrity and security, uniform way to administer data. Most importantly, concurrent access, recovery from crashes, persistence, scalability, portability. So I'm going to skip this evolution because not so important. So DBMSs have been around for more than 40 years. And they have worked very well. Today, they work behind the scenes. Earlier, people were using it directly. But today, because of the GUI and the web and other things, what you do on the web is likely to get translated as a query to a DBMS behind the scenes, and then you get the results presented. So used for payroll, airline reservation inventory, certainly by Amazon, eBay, everyone. They serve well for efficient storage of large amounts of data. However, expectations keep changing. So some of that brings us to, so I'm going to sort of skip a couple of these that are not important from your perspective. So let me cover. So as I said, databases are behind the scenes. What you essentially do is to fill a form, and what you get is a result. So how does this happen? Actually, the data is actually stored in a database. This is converted into an SQL query, and the retrieved results are also shown in some way. So it's not that there is something else. So this is very true today. Almost every system behind the web is some kind of database, multiple databases from which information is retrieved. So the relational model became popular because of its simplicity. It has a model, which is a set. It also has a set of operations that are set operations like union, intersection. This is also based upon the mathematical notion of sets, which makes it sound. A relation can also be viewed as a table, rows and columns. That's why one thinks that it is very popular because, I mean, of course, this came about even before spreadsheets and other databases. So it looks like a spreadsheet, can be seen as a spreadsheet, although was used much earlier. So this is how it looks like. So you can look at a relation of a student saying it is the student ID, name, login, age, GPA. So it's easy to understand, easy to think of, but designing that may or may not be that easy. Why is it popular? Easy to use query language. So you use SQL, known as the structured query language. It's a very powerful associative query language. Programming and understanding data storage formats not required. So you don't need to worry about programming your queries. You have to write it in SQL, which is much easier. It also does a lot of optimization that is difficult to do by the end user. Data and metadata are represented in the same format. Very importantly, supports multiple users recovery. In SQL, just to give an example of why SQL is different from programming, you can ask a query like list female students in the College of Engineering whose GPA is greater than 3.8. Now, this is a kind of you're expressing what to retrieve and not how to retrieve. Now, this query, when translated into SQL, which becomes 2 lines of translation, will be converted into an algorithm by the underlying system and the result obtained and shown as a table. That's why it's so popular. You can also say list all students in the CS department in 2022 who got A from every course they took under instructor B. So this is a more complex query than this one, but it can also be easily written in SQL. Generate a report listing average salary of faculty in each department of the College of Engineering for comparison. Of course, these need to be written as SQL queries, but that is much easier than writing a program. Now you can even do it with GUI. So if there is an interface, you can just fill up these values that you are interested in, and then the query can be generated. So burden of efficient retrieval is on the DBMS, not on you. However, relational DBMSs, all DBMSs need a schema. So you have to go through the modeling. Schema is nothing but a description of a table. So once you go through the modeling, you describe the table, but what you have is the relation or a table that you are going to use. So again, the same table, but this is how you specify to the system, but this is spit out by the program. You don't have to write it. You do the ER diagram, and this can be automatically generated from that, and then you load it to the database, so life is simple. So it supports a bunch of data types. They have been adding date and time have been added, not geared for voice, image, logs are stored as files, links to the files. Regarding the commercial DBMSs, there are only 3 main commercial DBMSs today. Oracle, DB2 is from IBM, SQL Server is from Microsoft. Sybase is still there, but has a very small market share. Public domain DBMSs, MySQL is very popular. You might have heard of that. Postgres is very popular and very widely used. DBMSs were optimized. There are still certain limitations, and there is still being expanded, added features are added. So the work is still going on. One other thing that comes into picture for any application is the scalability. How do you scale? Is it possible to add more juice to your processing, more horsepower to your processing? Is it possible to use more storage to your processing, your system? So that is the kind. So one is adding disks to enlarge the amount of data that you want to store. One is adding more processing power. The question is, both are a little bit difficult with relational DBMSs because a lot of things need to be reorganized, redone based upon that. That's why, if you're familiar with it, MapReduce and other things have come into picture mainly because of it. So to summarize the relational module, a tabular representation, simple and intuitive, powerful and easy to use, can scale, lots of utilities available. Object-oriented DBMS features were incorporated into relational DBMS, making them, so earlier, all object-oriented DBMS were developed as separate systems, but today they have been rolled into relational DBMSs. Briefly, a couple of slides about data warehousing. So data warehousing can also be seen as a repository, but it's a special kind of repository used by an individual organization for a specific purpose. So why do we need data warehouses? So by the time the need for this came about, DBMSs were mature. Enterprises used multiple DBMSs many times from. So this is very important to understand. Even within an enterprise, because of the merger and acquisitions, you may have different companies coming together which are using different DBMSs, or within the same organization for different reasons. You may be using Oracle for one unit, DB2 for another unit, and that's why hence you have multiple. They could also be heterogeneous. Queries could not be posed across DBMSs. So if you want to ask a query across many DBMSs, that was very difficult, not possible. Analysis and report generation using multiple DBMSs were also a problem. So data warehouse was proposed as a solution. So what does the data warehouse do? Essentially, it aggregates information from multiple DBMSs and puts it into a new DBMS. So this DBMS typically has a different schema. We will not go into the details of that schema. So there is an integrator. There is metadata that's associated with it. There are individual DBMSs. So this is not as simple as it looks because these sources are changing continuously. They are being updated. So there has to be a lot of technology to make sure that information is integrated. And now the report generation and analysis can be done on the data warehouse instead of individual sources. You can still query individual sources for what it contains, but you can also write queries across these sources. That's very important for an enterprise. So you can make a complete decision support system using this technology. So you have information sources, you have data warehouse servers, you have what we call OLAP servers, multidimensional OLAP and relational OLAP, and then you can do analysis, query reporting, data mining. So this is used today. This has become it has become a prime time product. Almost every DBMS vendor supports a data warehouse. So today, earlier were developed as separate systems. Today, all major vendors support data warehouses. So data marts are smaller forms used for specific purposes. Data lakes, unrelated, or storage repositories that mainly store data. In the interest of time, what I'm going to do is to skip cloud computing and go into something that's more, you can look at it if you need. So I want to give a little bit of introduction to GIS, which is the Geographic Information System that may be more closely related to your area of your domain and research. Is a multi-component environment used to create, manage, visualize, and analyze data and its spatial counterpart. So the emphasis here is, so what we were doing in relational and our databases was only the data component. Here you have a spatial component that you need to, that makes it more complicated. Spatial queries and spatial renderings are not as easy. Most data sets can be assigned a spatial location, typically in the form of lat-long. Does your data need to be analyzed in a GIS element? It depends upon how you want to understand them. So many times, visual analysis rather than a report is much better in terms of understanding. So here is an example. So here is a table that indicates just index of total African conflict for the period that is taken from somewhere. If you have this data, and if you want to ask a question, identify top 4 countries with highest conflicts. This is relatively easy to do. This can be done in a traditional TBMS by writing an SQL query that will give you that result. But if you want to find whether the high conflict countries are geographically clustered or whether there is a geographical relevance for this one, that's very difficult to do from this table. So that's where the spatial component comes into picture. So if you render the same data, for these spatial elements of data should be readily accessible in regional form. This is difficult to accomplish with tables and spreadsheets. So here you can map it in different ways, which gives you a much higher or better understanding of the juxtaposition of regions. And if you are really interested in knowing the high conflict countries, you can know whether they are next to each other or not next to each other in whatever way. So kind of a more complex data storage mechanism is required because storing lat long and spatial information is not the same as storing, and also processing is not the same. This is the core of a GIS environment, a spatial database that facilitates the storage and retrieval of data, that define the spatial boundaries, lines or points and polygons, the entities we are studying. This may seem trivial, but without a spatial database, most spatial data exploration would be very difficult. So these are a couple of definitions from different uh, uh, entities. USGS is one of the major force in this area. SV is one of the companies that has been doing GIS development for a long time. They have a lot of products. All the ARC products comes from them. So in the strictest sense, a GIS is a computer system capable of assembling, storing, manipulating, and displaying geographically referenced information, data identified according to their locations. This definition is not very different, but in terms of different technologies. GIS software, many GIS software applications are available, both commercial and few open source. Two popular applications are ArcGIS and QGIS. ArcGIS, developed by S3. This is a desktop environment and encompasses a suite of applications which include ArcMap, ArcCatalog, and various others. So one thing you have to understand, all of these use traditional DBMSs where it is appropriate and has added other components to the database in order to store and manage spatial information and also process additional information on top of that. ArcGIS Pro can run on Mac using virtualization. QGIS is an open source. It encompasses most of the functionality. If you're looking for a GIS application, QGIS is a wonderful choice. Built into the current version of QGIS are functions from another open source. GRASS has been around since the 80s and has many advanced GIS functions. However, its use is not as intuitive as that of QGIS or ArcGIS, hence the preferred QGIS alternative. So what is the difference between these DBMSs and traditional DBMSs? Software and data. You need different software packages. So central to this is the GIS application package. Such software is essential for creating, editing, analyzing spatial and attributing. Therefore, these packages contain a myriad of GIS functions inherently. So again, this is how one has extended built upon the facilities that were available, because if you had to develop this from scratch, then you have to worry about staging, you have to worry about buffer management, you have to worry about optimization. Extensions or add-ons are software that extend the capabilities of GIS software. Component GIS software is the opposite of application software. Component GIS seeks to build software applications that meet a specific purpose and thus are limited in their spatial analysis. Utilities are standalone programs that perform a specific function. For example, a file format utility that converts from one type of GIS file to another. There is also a WebGIS. So these have been added. I'm not totally familiar with a lot of these things, but I think you may be able to, you may be more familiar with it. Geodatabase. So there is a geodatabase underneath is a collection of geographical data sets of various types held in a common file system folder or a multi-user relational database management system, such as one of the traditional systems. Data is the core of any GIS. There are two primary types of data that are used. You should be familiar with that: vector data and raster data. So there are differences between these data, so at least you need to know which format it is in from the application perspective to render it properly. Coupled with this data is usually known as the attribute data. This is a relational DBMS that we have introduced. Attribute data generally defined as additional information about each spatial data. housed in that one. So you can also think of that as the metadata. Documented metadata contains such information as coordinate system, when the data was created, when it was last updated, who created it. So it also includes some provenance and how to contact them and definitions. So we will see this in the second half of today. To summarize, ArcGIS Desktop consists of several integrated applications, including ArcMap, ArcCatalog, ArcToolbox, and ArcGIS Pro. ArcCatalog is the data management application. Several software extensions can be added to ArcGIS Desktop that provide added, including 3D analyst, spatial analyst, network analyst survey. From the end user's perspective, ArcGIS has very wide-ranging functionality. So mostly you will be using this as an end user like the other one. You're not most likely to develop this system or the software associated with that. So I am thinking what to do. So these newer applications, I'm not sure how critical they are for our purpose. So my thinking is that I'm going to skip this and take a break and come back. So before that, what I want to, let me see if there is anything that should be. Okay. So let me just summarize and so we can take a break. In addition to the databases discussed, there have been several other types. I'm just mentioning it for completeness. Spatial representation and computation perhaps are the most relevant to your domain. Databases also support other properties that we did not have time to discuss. Supports concurrent users and recovery. Indexing is used. Mirroring and hard standbys are used for mission critical. So this is very important. The important thing is when 9/11 happened, lots of financial institutions that had their servers in those buildings did not lose any data, mainly because of mirroring and hard standbys. Typically, when you have mission critical database, you want to make sure that that database is mirrored somewhere else in a different geographic location. So if something happens, a tornado hits one place, the data is destroyed. And hard standby is very important because hard standby means both the copies are being updated at the same time. Otherwise, one will lag behind the other and you will not have the complete duplication in real time. So this is very important. I don't know whether this is as critical for your applications, but in many financial and other applications, this is extremely important and need to be supported. So I'm going to stop here and take some questions, and then we will have a 15-minute break and come back and continue with the other two modules. So now the time is 10:35. So 10:40. So we'll come back at 10:50. Okay, I'll see you. So take a break, stretch yourself, and do whatever you need to do, and we'll be back. Thank you.